Hello everybody, today is Tuesday, March 20th, and I have a great science video for you, and as well I want to do a secret science video. Let's talk about the regular science first. We have several different things that I want to discuss. Today, let's start with the flat earth thing. So people have been some people are just seeking attention, but there are a growing number of young adults and teenagers who maybe they don't have the IQ to understand perspective, or perhaps they've just not been taught well about things. Like they'll show an image and it'll show like an airplane and be like, the airplane would constantly have to nose down, but the airplane that they're using would be like the size of Texas. So here's a way that you can easily explain to anybody who is seriously, not just for attention, but seriously proposing a flat Earth, which, by the way, Ptolemy's model cannot predict eclipses. So if you ever see anybody out there saying they can predict comets and eclipses, it cannot, and that's one of the reasons why it was overturned. So if you have a basketball, if the Earth was shrunk down to the size of a basketball, how big do you reckon that you would have to be as a human to be in proportion with the new Earth, right? Would you have to be the size of a flea or an amoeba? Right? And even at an amoeba size, just imagine, you can't see any of the bacteria and amoeba that are on this basketball right now. But if you could imagine yourself the size of an amoeba, it would be still quite a flat thing. You theoretically might be able to see curvature, but pretty much it would seem flat. Well, actually an amoeba would be like Godzilla. You would need to be smaller than a flu virus, much smaller than HIV, right? You need to be smaller than a flu virus. So now, if you can imagine a virus, I don't know if you've seen electron microscopy, but if you can imagine a virus, if you were that size on this basketball, it would fit easily within these little grooves, like well within. These grooves would be canyons. It'd be like Grand Canyons. They'd be like Peruvian canyons to you. You would not be capable of discerning the curvature from a flat perspective. All right, bear that in mind. So when you meet somebody who professes to really, truly believe in flat Earth, ask them, how big, if the Earth was a basketball, how big would they be in comparison? Because I don't think that they realize, when you talk about scale, just how big the Earth actually is. I think probably it's a problem of the internet shrinking our world. You ever heard that idea, it's a small world after all? That's a human world, right? Not the actual world. The actual world's huge. The human world's small. And you might meet people and it's just unexpected, who knows who. But the physical world is massive. There are still massive amounts of places where there's very few humans at all, and they're very harsh environments, much harsher even than Death Valley. So whenever you meet somebody, be sure to give them a heads up about that. What else did I want to talk about? Oh, give you an update. Orion's busy working on his skyscraper. Check out, it's it's not even a whole wall, right? He's got a 5-layer design. But I wanted to point out, one of the hard things about working with popsicles is you can have a great design. This is he's got a Y design on this side and a V will be on the back. But look at the way that bows and curves like that. It's a nightmare for fixing, for turning walls into actual structures. So, interesting thing about structure. I brought back the Stirling engine. So, you'll remember, you use a hot water source, or you could use dry ice. You could do extreme hot or cold, and then you set that on there, and then we'll let that warm up. I want to talk in general about the yin-yang function of transfer of heat. The most energy comes from higher gradients. So wherever in the universe you find extreme gradients of a lot of cold or a lot of heat, you will find a high potential between them. And that might be a mechanical potential, a thermal potential. It could be, of course, thermal shock, right? It's that, if you have a really hot object and you put it into cold water, it can explode, or it can break, shatter, crack. Also, if you have stored up chemical charge and you suddenly crush The chemical, especially sugars, you can generate lightning. Like there are possibilities, or even just when you have something that moves really fast underwater, you can create cavitation, and that cavitation can introduce thousands of degrees worth of temperature. Obviously, it's not thousands of degrees. That's a misnomer, but people are misunderstanding. It's not actually thousands of degrees Celsius or Kelvin inside the cavity. It's just that when you calculate what it would be if the cavity were to remain, the temperature would be vastly larger, and that creates a lot of energy, creates a shock wave that you can hear. So it's clear that when you have a gradient, the amount of energy between is all dependent upon the extremes. So you can say, an obvious example would be a boulder rolling downhill. The bigger the boulder, the more damage it can do at the bottom of the hill. This is really quite common sense. So we take a look at here the Stirling engine. We have hot water, we have chill air above, and if you remember correctly, of course, we have to help it get started, and then it's able to maintain its, let's see here, there we go. Fully green energy, right? It's run just by a thermal gradient. So where am I going with this? We don't really truly understand heat and thermal issues. We have a light-based model, and although heat is infrared, our understanding of how it moves and how it conducts is not precisely how it works. It is very close, and of course it's very convenient. You know, you talk about metal. Metal's more conductive. Take, for example, cold. We have a thermodynamic model. We call the 5 laws of thermodynamics, the 3 original ones, and then there's 2 other ones. But we say that the heat is conducting through the metal, so the metal feels cold to our skin because there's a greater amount of thermal conductivity versus, say, this table, right? Now, that's not the only way that cold exists. It seems like it to us, and I wouldn't argue the point with anybody who's tied very heavily to Western science, because for them, cold is only a lack of infrared energy. But the interesting thing I find about it is that this object is shiny, and it does reflect IR. So if you have a shiny metal object, you can get thermal reflectivity, and you can measure that with a thermal camera, and yet you can still heat up the metal. Now, you can't heat it up as well as with the other, as with, like, say, a dull piece of steel. However, you still have this tendency to heat when in an object that is clearly reflective. And vice versa, when you have, like if you're thinking about magnetism, when you have a transformer, they often use a square shape, right? However, if it was really in flux, if it was really a flow in the magnetic field, it should be oval or perhaps even just kind of beveled around the corners. And yet that's not necessary. There is something interesting happening where there's an interaction between the EMF field that we call light and the whole spectrum and the actual the atoms, the substance, the matter. And that is illustrated by definitely 2 different phenomena. One would be superconducting, which I mentioned before. Suddenly you drop something below just an arbitrary temperature, seems like to us, arbitrary. And suddenly it has 0 resistivity. Makes not much sense. And then you have black body. And black body, whether it's black body radiation or the absorption of radiation, is a strange effect, all considering the need to actually conserve energy, because my assumption is that no matter what, the law of conservation is definitely true. So the law of conservation of momentum, law of conservation of energy, that things have to be conserved. All the equations have to be there, which tells me that we are probably missing something about the electromagnetic property and how it interacts with matter, because matter is electromagnetic, because E equals mc squared, which is it's an electromagnetic derived model, that there is something going on that's far more interesting. Now, what that is, I don't know, and I'm probably not the smartest guy to go and discover that. I don't think that I'm destined to figure out what that is. It might be a complete mystery throughout mankind's history. I don't know. We seem to be spending a lot of money on looking for particles that really have no particular use for our daily life, how to improve our life. And yet, there's something as simple as electromagnetism, which this is electromagnetism, right? We have thermal radiation. We call it thermal, but it's really infrared. And the infrared is a spectrum of light. And it's creating, because there's a heat gradient from the cup to the air, there's a alternating compression and expansion of the gases inside the piston. And as you can see, the thermal energy that was initially put into the water by electricity, in this case, from the spout. No, I didn't boil it, I used the other. But from the electricity into, then there's all this potential energy stored as extra infrared, and it is slowly heating up this container, and the gradient generates the mechanical power. Just wonderful. It's almost like magic when you watch it, because we're so used to, you have to burn something chemically to get, burn wood, burn gasoline to get an explosion, and you don't. We just need to understand electromagnetism more. As you know, it's slowing down because it's getting warmer. The bottom part of the piston is actually warmer. So anyways, that's what I had to say about gradients. That the gradient is what's really the issue. If we can find a way to get a gradient, I would recommend everybody go over to, first of all, go watch the new Electric Universe video about structured atoms from the EU 2017 talk. The more I study it, the more I'm convinced that atoms are actually shaped internally, not randomly, but like platonic solids. And that spin is not really spin so much as various surface arrangements of those platonic solids. It makes total sense. I mean, there's something alluring anyways to our minds about the platonic solids, but I think that it's the reduction, it's the simpleness of it, right? Following Occam's razor. And I have a feeling that therein lies our salvation, if you will, as far as energy needs, that through lasers and through electromagnetism, we will be able to induce changes in a distant object. Obviously, it would start in a lab, that would cause arrangement or rearrangement of those solids inside, and to create charge potential differences and induce a plasma arc from a region of high potential energy and high charge to a region of low voltage, right? So place high voltage to low voltage by sending a signal, and that signal, of course, a signal is just another way of saying an electromagnetic wave, okay? And sending that signal and inducing those atoms to rearrange themselves. We've provided the energy in the laser, but we've encoded, we've modulated the signal to rearrange the atoms to cause them to release their charge and go from a state. This is sort of like when you have plutonium or uranium. It could be laying around the ground. But if you rearrange it and you put it together, it spontaneously releases energy. This happens in chemistry all the time. You don't always need a catalyst. You do need an initiating activity to change the system. Although there are reports, of course, of spontaneous chemical reactions in nature, but I think there's always got to be an initiating cause, pretty much. So we can initiate, and then boom, we can get a plasma discharge from a place of high energy, and maybe we bounce it through, an asteroid or off of a planet and get it to here. I think that that's ultimately how we are going to find the energy source that we need to truly space travel. Now, I don't know what century that would be, and I certainly am interested to see anybody do that kind of research. The structured atom model is very new, so I don't know how close it is to even being accepted. It could take 100 years all by itself. Plasma electricity has been with us longer than relativity, and as people still don't understand it. And speaking of which, the video today, the Secret Science video, is going to be related to plasma. So I hope you tune back and watch the other video. We're going to be talking about the fire element. Okay, and you all have a great day. Like, share, subscribe, and I hope to see you again next time.